to the lesson on quadrilaterals and its types. At the end of this lesson, you will be able to identify different kinds of quadrilaterals based on their shapes. You will also be able to verify properties of various kinds of quadrilaterals and the angle sum property of a quadrilateral. Look at these points on a plane. Consider any 4 points such that no 3 points lie on the same line. Join the points in a clockwise or anti-clockwise direction. What do you obtain? A 4-sided closed figure. This is called a quadrilateral. A quadrilateral has 4 sides. Here AB, BC, CD and DA are the 4 sides. 4 angles, angle A, angle B, angle C and angle D are the 4 angles formed at the vertices. And 4 vertices, A, B, C and D are the 4 vertices. AC and BD are the 2 diagonals of the quadrilateral ABCD. Next, we'll discuss about the different types of quadrilaterals and their properties. Quadrilaterals can be classified into different types based on their sides and angles. Let's learn about each of these quadrilaterals. You are already familiar with the first 2 quadrilaterals. Yes, the first quadrilateral is a square and the second is a rectangle. Each angle of these 2 quadrilaterals is a right angle. Also, the opposite sides in each case are parallel. The difference is in the lengths of their sides. A square has all sides equal in length, while a rectangle has opposite sides equal in length. The diagonals of squares and rectangles bisect each other. In case of a square, they bisect at right angles. Thus, a square is a rectangle with adjacent sides equal. Next, let's consider the third quadrilateral. If we compare it with the rectangle, we see that it is different from the rectangle in terms of the measure of its angles. Its angles are not right angles. However, the opposite angles are equal. Such a quadrilateral is called a parallelogram. Let's define it. A parallelogram is a quadrilateral in which opposite sides are parallel and equal in length. Opposite angles are equal. Diagonals bisect each other. Now, consider the fourth type of a quadrilateral. On comparing this quadrilateral with a square, we find that most of their properties are same. However, unlike the square, its angles are not right angles. Such a quadrilateral is called a rhombus. A rhombus is a quadrilateral in which all sides are equal in length. Opposite sides are parallel. Opposite angles are equal. And diagonals bisect each other at right angles. Thus, we can say a square is a rhombus in which each angle measures 90 degrees. Now, let's consider the definition of all 4 quadrilaterals. Can we say that a square, a rectangle and a rhombus are parallelograms? Yes, we can. Squares rectangles, and rhombuses are all examples of parallelograms. Thus, squares, rectangles, rhombuses, and parallelograms can also be defined in terms of quadrilaterals as shown. The relation between these can also be represented as shown. Now let's consider the remaining quadrilaterals. Both these quadrilaterals are quite different from the ones we have just learned. This is a trapezium. It is a quadrilateral in which one pair of opposite sides is parallel. Now, here's a special trapezium. Its non-parallel sides, as you can see, are equal in length. Similarly, if you measure the base angles, you will see that both are equal. Thus, a trapezium having non-parallel sides equal and base angles equal is known as an isosceles trapezium. Now, let's consider the last quadrilateral. Does this shape look familiar? Yes, it is similar to a kite you must have seen flying in the sky. This quadrilateral is called a kite. Let's learn more about a kite. A kite is a quadrilateral in which two pairs of adjacent sides are equal in length. And one pair of opposite angles, the ones that are between the sides of unequal length, are equal in measure. Also, one diagonal bisects the other. And diagonals intersect at right angles. Now, let's prove a property which holds true for all types of quadrilaterals. Do you remember the sum of three angles of a triangle? Yes, it is equal to 180 degrees. Using this property of a triangle, we will show that the sum of four angles of a quadrilateral is equal to 360 degrees. Consider a quadrilateral. A diagonal divides it into two triangles. Since the sum of three angles of each triangle is 180 degrees, the sum of the angles of a quadrilateral is equal to 360 degrees. Let's prove this theorem. Consider quadrilateral ABCD. Let AC be its diagonal such that it divides the quadrilateral into two triangles, triangle ABC and triangle ADC. Sum of three angles of a triangle ABC is equal to 180 degrees. That is, angle BAC plus angle B plus angle BCA is equal to 180 degrees. Similarly, the sum of the angles of triangle ADC is equal to 180 degrees. That is, angle DAC plus angle ACD plus angle D is equal to 180 degrees. Adding equations 1 and 2, we get the sum of the angles equal to 360 degrees. But angle DAC plus angle BAC is equal to angle A. Similarly, angle ACD plus angle BCA is equal to angle C. This implies angle A plus angle B plus angle C plus angle D is equal to 360 degrees. Thus, the sum of the angles of a quadrilateral is equal to 360 degrees. That is, the sum of all the angles of a square, a rectangle, a parallelogram, a rhombus, a trapezium, and a kite is equal to 360 degrees. Welcome to the lesson on properties of a parallelogram. At the end of this lesson, you will be able to identify the different types of parallelograms and illustrate the relationships between them. You will be able to state and prove different properties of a parallelogram. You will also be able to prove that a diagonal divides a parallelogram into two congruent triangles. Let's first quickly recapitulate about parallelograms and their types. A parallelogram is a quadrilateral in which opposite sides are equal and parallel. Rectangles, rhombuses, and squares are all different types of parallelograms. A rectangle is a parallelogram in which any one angle is of measure 90 degrees. A rhombus is a parallelogram in which all sides are equal. A square is a rectangle with all sides equal. Now, let's learn about the properties of a parallelogram with the help of an activity. First property we are going to prove is that a diagonal of a parallelogram divides it into two congruent triangles. Consider this parallelogram. Let's join any of its two opposite vertices. It divides the parallelogram into two triangles. The two triangles coincide, means the corresponding sides of both the triangles are equal. This implies a diagonal of a parallelogram divides it into two congruent triangles. Since the triangles are congruent, their corresponding sides and angles are equal. Thus, we conclude that in a parallelogram, opposite sides are equal and opposite angles are equal. Let's now join its other two vertices. It divides the parallelogram into four triangles. Consider these two. On placing one over the other, you will notice that they also coincide. This implies that the corresponding sides are equal. Thus, we can say that the diagonals bisect each other. Now, let's check that the properties of a parallelogram also holds true for rectangles, rhombuses, and squares. Let's draw any one of their diagonals. You will notice that in each case, a diagonal divides it into two congruent triangles. Thus, all the properties of a parallelogram holds true for rectangles, rhombuses, and squares. Let us now try to prove some of the properties of a parallelogram. First theorem we are going to prove is a diagonal of a parallelogram divides it into two congruent triangles. Consider a parallelogram ABCD and let AC be its diagonal. In order to prove that the diagonal AC divides the parallelogram into two congruent triangles, we will prove that triangle ABC is congruent to triangle CDA. In triangle ABC and triangle CDA, angle BCA is equal to angle DAC. Since AD is parallel to BC and AC is a transversal, they form a pair of alternate interior angles. Also, angle BAC is equal to angle DCA. Since they form a pair of alternate interior angles, full AB parallel to DC and AC being a transversal. Side AC is common to both the triangles. Thus, from equations 1, 2, and 3, two angles and the included side of triangle ABC are equal to the corresponding two angles and the included side of triangle CDA. This implies triangle ABC is congruent to triangle CDA by the ASA congruence rule. Thus, a diagonal of a parallelogram divides it into two congruent triangles. This completes the proof. Now, continuing with same parallelogram, which is divided into two congruent triangles. By CPCT, we can say that the corresponding sides of the two congruent triangles are equal. That is, side AB is equal to DC and side AD is equal to BC. Thus, we conclude in a parallelogram, opposite sides are equal. Also, corresponding angles are equal. That is, angle B is equal to angle D. Similarly, on drawing the other diagonal, we get angle A is equal to angle C. Thus, we conclude in a parallelogram, opposite angles are equal. Now, let's prove the second theorem. If each pair of opposite sides is equal in a quadrilateral, then it is a parallelogram. Let ABCD be the given quadrilateral in which AB is equal to CD and BC is equal to AD. To prove quadrilateral ABCD is a parallelogram, we will show that a pair of opposite sides is parallel. Draw diagonal AC. Let's begin with the proof. In triangle ABC and triangle CDA, side AB is equal to side CD, denoting it by equation 1. Side AC is common to both the triangles, denoting this by equation 2. Side BC is equal to side AD, denoting it by equation 3. Thus, the three sides of triangle ABC are equal to the corresponding three sides of triangle CDA. Therefore, by the SSS congruence rule, triangle ABC is congruent to triangle CDA. Now, since the corresponding parts of congruent triangles are equal, therefore, angle BAC is equal to angle DCA. And angle BCA is equal to angle DAC. On adding, we get angle A is equal to angle C. Also, angle B is equal to angle D by CPCT. That is, opposite angles of the quadrilateral ABCD are equal. We know that a quadrilateral is a parallelogram if the opposite angles are equal. Hence, the quadrilateral ABCD is a parallelogram. The third theorem we are going to prove is, if the diagonals of a quadrilateral bisect each other, then it is a parallelogram. Let ABCD be the given quadrilateral in which diagonals AC and BD bisect each other. This implies BE is equal to DE and AE is equal to CE. We have to prove quadrilateral ABCD is a parallelogram. Let's begin with the proof. In triangle AEB and triangle CED, we are given side AE is equal to side CE, denoting this by equation 1. Angle AEB is equal to angle CED, since they form a pair of vertically opposite angles, denoting this by equation 2. Also, side BE is equal to side DE, denoting this by equation 3. From the above equations, two sides and the included angle of triangle AEB are equal to the corresponding two sides and the included angle of triangle CED. Thus, by the SAS congruence rule, triangle AEB is congruent to triangle CED. Now, since corresponding parts of congruent triangles are equal, therefore, angle ABE is equal to angle CDE, which are the alternate interior angles for lines AB and DC and transversal DB. Thus, AB is parallel to DC. Also by CPCT, AB is equal to DC. Thus, in the quadrilateral ABCD, we have a pair of opposite sides equal and parallel. Hence, it is a parallelogram. Welcome to the lesson on the midpoint theorem. At the end of this lesson, you will be able to state and prove the midpoint theorem. You will also be able to solve problems based on midpoint theorem. Three friends, A, B, and C, are standing on the three vertices of a triangle. Two more friends, D and E, joined them and stood on the two sides AB and AC, such that they position themselves midway. D and E claim that the perpendicular distance between the line joining them and the line BC remains constant. That is, line DE is parallel to the line BC. Let's check if they are speaking the truth. Measure angle ADE and angle ABC. They are equal. This implies that the corresponding angles formed by the lines BC and DE with the transversal AB are equal. Thus, DE is parallel to BC. Also, D and E claim that the distance between them is half the distance between B and C. For this, let's measure the length of the line segment DE and BC. Wow! They are right. Finally, friends D and E have successfully claimed that if they stand midway between the two sides AB and AC of a triangle ABC, then DE is parallel to BC and DE is half of BC. In geometry, this result is known as the midpoint theorem. Let's prove it. The line segment joining the midpoints of the two sides of a triangle is parallel to the third side and equal to half the third side. Let ABC be the given triangle in which P and Q are midpoints of sides AB and AC respectively. We have to prove that line PQ is parallel to side BC and PQ is half of BC. Draw a line CR parallel to BA such that it meets PQ produced at R. Here, we'll prove that the quadrilateral BCRP is a parallelogram. Let's begin with the proof. By construction, we have drawn CR parallel to BA, and from the figure, AC acts as a transversal for them. This implies angle QAP is equal to angle QCR, as they form a pair of alternate interior angles. Denote this as equation 1. Also, AQ is equal to QC, since Q is the midpoint of side AC. Also, angle AQP is equal to angle CQR, since they form a pair of vertically opposite angles. Thus, two angles and the included side of triangle APQ are equal to the two angles and the included side of triangle CRQ. Thus, by the ASA congruence rule, triangle APQ is congruent to triangle CRQ. Now, since the corresponding parts of congruent triangles are equal, PQ is equal to QR, or PQ is equal to half of PR. Also, AP is equal to CR, but AP is equal to BP since P is the midpoint of the side AB. This implies BP is equal to CR. Also by construction, BP is parallel to CR. Thus, in the quadrilateral BCRP, we have a pair of opposite sides, BP and CR, that are equal and parallel. This implies quadrilateral BCRP is a parallelogram. Now, since opposite sides of a parallelogram are parallel, BC is parallel to PR, or in other words, BC is parallel to PQ. Also, opposite sides of a parallelogram are equal. Therefore, PR is equal to BC. Therefore, half of PR is equal to half of BC. Or, PQ is equal to half of BC. The converse of this theorem also holds true. It says, the line drawn through the midpoint of one side of a triangle and parallel to another side bisects the third side. That is, if in a triangle ABC, P is the midpoint of AB and PQ is parallel to BC, then AQ is equal to QC.